Hello, everyone. First, I also want to thank the LLVM student travel grant to support me to be here and present my work. So my name is Yifei. I'm a PhD student at the KTH Royal Institute of Technology. And today I'm going to talk about leveraging MLIR for loop vectorization and GPU porting of the FFT libraries. And this work is done together with two of my supervisors, Arthur Pudobas and Stefano Markidis. So here's the outline. First is the motivation. Why do we need a new FFT library? And then I will introduce a little bit about our domain-specific language as a front-end, and also the FFT dialect we have introduced as an abstraction level. And later on is the challenges we have been facing when we're trying to utilize the MLIR and the LLVM to generate high-performance FFT code, such as the sparsity, the complex number we need to handle, and also how to find parallelization out of the FFT algorithms. And at last is the progress and plans. So first, the FFT, which is short for the fast Fourier transform, is actually plays a very important role in many applications, such as in signal processing. We can use the FFT to convert the signals from time domain to frequency domain. And also in numerical analysis, we can utilize FFT to perform the partial differential equations. And over the years, many FFT libraries have been developed, both from the industry and from the academic. So the motivation, first, some of the libraries are handwritten, so they may require significant efforts to develop and maintain. And also for the compiler-based libraries like FFTW, FFTW was developed like long times ago, so it's kind of lack of the portability over heterogeneous hardware. And also, they cannot utilize the evolving compiler infrastructure we're having now, such as the MLIR and the LLVM. And also the FFTW, it is a source-to-source compiler, so it will emit C-level code. And so it may lack of control on the low-level compilation. So here I will very briefly introduce the FFT algorithm. A direct computation of the discrete Fourier transform would be a matrix multiplication between the DFT matrix and the input vector. So the fast algorithm, the basic idea is to decompose the DFT computation into smaller DFTs. And we can, in the middle is the most famous Cooley-Tokay FFT algorithm. And in the bottom, we can see the representation in matrix form. We can see that after the decompose the DFT computation on the left, which is dense, and after the decomposition, now it has become several sparse and structured matrix. So we can take advantage of that and reduce the complexity. And here from order n squared to n log n. And here we introduced a domain-specific language for the FFT for the users to try different FFT algorithm easily. We try to design it to resemble the mathematical representation as much as possible. Yeah, I will not go to details here. And also we have developed a FFT dialect. Here we defined and implemented operators needed to represent different kinds of the FFT algorithm, such as we have introduced the Kronecker product, the Twiddle factor, the DFT matrix generator, and also the permute operation. And one of the challenges we're facing is how do we achieve sparsity. So here we can see from the left, here are some computation patterns in the FFT algorithm. And we can get that representation both from the domain-specific language in the front end and also from the FFT dialect in the MLIR. So we have introduced a high-level transformation in the MLIR on the FFT dialect called sparse fusion. So it will first match those patterns, and then it will fuse them to specific single operators, as shown in the middle. And then after the bufferization, we map those operators, we implement those operators using affine loops. We use a matrix-free method to achieve the sparsity. And here's an example, how do we get affine parallel loops out of a Stockham FFT algorithm. On the left, here is a computation pattern. which is the Kronecker product between DFT matrix and the identity matrix. And above is the memory access pattern. Actually, there is the vector parallelism out of this pattern, and the Stockham FFT have several stages of that kind of pattern. So first we apply sparse fusion to fuse them into single specified operators, and then we perform the bufferization to generate affine loops. And here we use a matrix-free method to generate the sparse computation. And also the generated loop are parallel because there is no dependency between different iterations, and also the memory access is consecutive, which is friendly for vectorization. And the other challenge we need to handle is the complex data. So the problem is that FFT algorithm needs to operate on complex data, but complex data is not a first-class type in LLVM currently, and also is not supported by most of the hardwares. So the biggest problem for us is that we cannot vectorize the complex data array in the MLIR level. So our solution is that after the bufferization at some level, we introduce several passes to convert the complex data to array of floats to lower the complex data type. So the benefits would be that now we can perform vectorization in MLIR, and also along the conversion, we can manipulate the data layout, such as we can generate the interleaved and splitted data layout. It's kind of, for the complex data array, it's kind of like the struct of array and the array of struct choices. Yeah, another important optimization is the vectorization. We have explored 3 different vectorizers. The first one is the super vectorize which operates on the MLIR affine loops. And the other 2 are the SLP and vplan vectorizer in the LLVM. So from a user's perspective, the most intuitive difference between the SLP and vplan would be that the SLP will operating on the innermost loop, and vplan is the outer loop vectorizer. And while we're performing the vectorization, one of the optimization we can perform on the fly is the interleaved memory access optimization. So because we need to access the complex array, we need to have the strided load and store. So by default, the compiler will generate gather and scatter. But because our stride is very small, it's kind of, in this case, the stride is only 1. So the alternative way is that we can generate consecutive load or store first, and then perform in-register shuffle. And in that way, we can eliminate the gather and scatter instructions, which are very expensive. So here are the, but right now the interleaved memory access is only enabled for the LLVM SLP vectorizer. So here we can show the example that we can successfully vectorize the code, but after the vectorization, the vplan vectorizer will generate gather instructions. But for the SLP, they can generate consecutive load and then in-register shuffle. Also, we can map our affine loop nest to the parallel hierarchy of the GPU hardware and generate GPU code. We have tried it on the NVIDIA hardware and generate CUDA binary. So to sum it up, our current pipeline in the front end, you can use either the domain-specific language we introduced, or we can using Python to generate the FFT dialect in MLIR. And then we can perform some high-level tensor transformations like the sparse fusion we introduced on the FFT dialect. And after that, we lower it down to the affine loops. And here we convert the complex type to the array of floats, which can enable us to more optimizations. And also we perform some affine optimization here, such as loop tiling and roll. And after that is the hardware-specific transformations, such as we try different vectorizers in MLIR and LLVM, and also we can map it to the GPU kernels. And for the performance, here the higher is better. First, we compare the performance with different optimizations combined On the left, actually, the most significant performance gain comes from the interleave with memory access I talked before. And on the right is the performance results comparison between different vectorizers. For now, the MLIR vectorizer performs the worst because in our case, the memory access pattern is not optimized. Yeah, it will generate scalar code. And the SLP vectorizer with the interleave memory access optimization performs the best. We also compare our work with the state-of-art FFT library, the FFT For now, we're still falling behind, especially for some sizes. Part of the reason is that for now, we haven't implemented the mixed radix FFT algorithm. So that means we didn't generate the most efficient decomposition plan or the most efficient algorithm for some FFT sizes. And also, it is a work in progress project, so there are some optimizations we have planned but haven't implemented yet. And also on the right is the GPU performance. Right now, we only have a naive implementation, so here just show the functionality. So for future work, we want to implement more optimizations and also support the more hardwares, and more importantly, we plan to have a runtime which can automatically generate different decomposition plans. Yeah, that's the end of my talk.
Hi, nice work. Thanks for presenting. I see you used affine and affine vectorizer. That has been basically dead since like 2 years. Have you looked at vector dialect instead? And like creating, when you start your FFT matrices, you can convert those to be a matrix of vector of complex instead of being a matrix of scalars that you need to vectorize. Basically, your code starts as being vectorized, then you devectorize and vectorize again, and that's going to be bad. So have you looked at like something of vector and creating vector types early in your pipeline?
You mean like utilizing like the linear algebra dialect and also...
Same approach, not using an LH, just similar approach to that.
Well, I tried before. It's like for now, the vector dialect doesn't support the complexity type. I don't know what happens now, but the time I tried didn't.
Just add a trait and it will?
Yeah, I know there's some hack to make it work, but the problem is that when lower it down to LVM, there isn't one-to-one map. I need to implement something like the lowering here, like to implement the complex, to lower the complex to a struct of of two elements. I need to implement that there when lowering down to LVM.
Okay, thank you.
Yeah.
So when you design the FFT dialect, can you talk about why you had like your own constant or own mapmul operator versus using what already exists in other dialects?
Yeah, actually, I want to reuse the operators which is existing in other dialects, but there are some specific operators which related to the FFT algorithm. We need to implement them specifically, such as how do we generate the twiddle factors, the DFT matrix, which is not available in the open source MLIR project.
I see like arithconst and identity and mapmul. Those, I would assume those exist somewhere else in a different dialect. So is there like something specific about FFTs that need their own specialized variant? Like, is there some semantics of the operation that are different?
Yeah, I see. We can kind of generalize it and implement it in other dialects like linear algebra too. Yeah, but for now, it's like for the easiest way for us is to wrap it down to FFT dialect so we can have whatever we need. And if we don't find it in the other dialects, yeah.
I noticed that everything is power of 2 sizes. Do you support non-power of 2?
Yeah, that's a very good point. For now, we only support the power of 2. The reason is, like I said, we didn't support the mixed radix size FFT now, and also we didn't support the random size FFT now. Mm-hmm. It's on the algorithm level. We need to work it out. Yeah.
Okay, thank you.
Could you go back to your plot with the GPU performance?
GPU performance is very bad, actually.
I was just thinking, since most big systems for scientific computing are GPU accelerated, like what are your steps to get better GPU performance? Do you have anything planned?
Yeah, for now, actually, we have very naive implementation. We just make it work to show that we have the functionality. Later, it's like, first is that we need to generate the tiling to map it more efficiently on the GPU blocks and threads, and also maybe the memory access optimizations, like promoting some of the memory to the local shared memories, things like that. But for now, it's very naive, just to show that it can work. Yeah.
Okay.
Yeah.
Thank you. I think follow up with more questions if you have. Let's thank all the speakers for great presentations. Thank you.